Since the beginning of the digital age, computing has relied on a single, inescapable physical reality. We process information by pushing electricity over metal wire. In the early days, getting more computing power meant building bigger machines to push more electrical signals through these pathways. For decades, this copper highway was perfectly fine for getting microchips to talk to each other. But to make computers faster, we had to shrink those copper wires down to microscopic scales, packing billions of connections into a space the size of a fingernail. Today, that 70-year legacy architecture is colliding with the hard limits of physics, stalling technological advancement. The breaking point arrived with the explosion of artificial intelligence. Modern AI servers and supercomputing clusters demand a volume of continuous data movement that early engineers couldn't have imagined. When you force massive amounts of electrical data through these microscopic copper wires, you create intense physical resistance. All that friction turns into heat. The thermal waste becomes so severe that data speeds must be throttled to keep systems from melting. The industry is stuck. We can't design our way out of a fundamental physics problem just by building better traditional electronic chips. To build the high-performance systems required for the future, we have to abandon the electron entirely and find a frictionless way to move information. The solution to this crisis is a technology called silicon photonics. This diagram illustrates the core concept. Instead of moving data using electrical signals, shown on the left, silicon photonics replaces electrical signals with light signals to move data inside computers, shown here on the right. Light offers massive physical advantages. It moves faster, requires a fraction of the energy, and travels without creating electrical resistance or heat. This is a highly engineered, microscopic translation process that occurs in real time. On this chart, the journey begins when an electrical signal arrives at the optical chip. A laser provides a continuous light source. Then, a modulator encodes that incoming data directly onto the light wave, which shoots through an optical waveguide. You can think of this waveguide as a microscopic fiber optic highway built directly into the silicon. The light travels to its destination, arriving at a photodetector which reads the optical information. In a fraction of a millisecond, the photodetector translates the light back into an electrical signal so the processor can execute the data. By running this electricity to light to electricity relay, engineers bypass the thermal bottleneck entirely, unlocking data speeds that copper wire simply couldn't handle. There is a common technical misconception about how this works. Silicon photonics is not designed to replace all the electronics inside a computer. Instead, it relies on a new approach known as hybrid architecture. In a hybrid system, there is a strict division of labor. Traditional electronic circuits still handle the logic, the actual thinking, while the photonics handle the communication. This diagram shows a modern circuit board. A traditional CPU shares the package with a new communication hub. Right in the middle is the photonic interconnect fabric, acting as a central optical transit hub, routing light signals directly out of the CPU. This fabric changes the layout of chip design, ensuring the CPU never sits idle waiting for data to arrive over slow copper wires. This high-speed light transit reaches every corner of the architecture. Optical links shoot outward, instantly connecting the CPU to memory and AI accelerators without lag. At the macro scale, these cables stretch between server racks, linking thousands of nodes into one unified supercomputer. While this architecture is starting in massive data centers, the technology is designed to eventually shrink down to power everyday, thin and light consumer laptops. By finally leaving the physical limitations of copper wire behind and trusting the flow of light, silicon photonics removes the thermal ceiling that has capped processing speeds for years.